Okay, hi everyone, welcome to our sixth tutorial. In this tutorial, we're going to review interpretations of t-statistics, confidence intervals, and p-values, and discuss some common errors in interpreting these. We'll then talk about the paired t-test and the Wilcoxon signed rank test, which are used when comparing the means of paired groups. And finally, we'll talk about the two-sample t-test and Wilcoxon rank sum test, which are used when you're comparing the means of independent groups. So first I'll start with a review of t-statistics. So you'll recall that test statistics tell us how far our sample statistic is from the hypothesized value for it in terms of the average deviation from the hypothesized value for the statistic, or the standard error. So whenever you're asked to interpret a t-statistic for the mean of a single population, it's critical that you interpret this as our observed sample mean of x for our sample is t-score standard errors above or below the population mean of x. So the t-statistic tells you how many standard errors your sample mean is from what you hypothesize the true mean to be. It's also important that you relate your interpretations to the context of the question or the example. So please try to be clear about the groups that are being compared and also whether or not you're referring to the sample mean or the true population mean in your interpretations. So an example interpretation would be our observed sample mean of 1991 calories for Vancouverites is 2.12 standard errors below the Canadian population mean caloric intake of 2,000 calories, which is what we hypothesize the true population caloric intake for Vancouverites to be. Our interpretation of a confidence interval depends on whether the mean and standard deviation are known or unknown. So whenever the true mean is known, our interpretation of a confidence interval is that we are 95% confident that we'll get a sample mean that is between the confidence interval. When the true mean is unknown, whether or not the true sample standard deviation is known, our interpretation is that we are 95% confident that the confidence interval will capture the true population mean. So we're using the information we have in our sample to derive an estimate of our true mean. So using an example from one of our previous tutorials, we are 95% confident that the true population mean caloric intake for Vancouverites is between the lower confidence interval limit and the upper confidence interval limit. If your confidence interval includes the true Canadian mean caloric intake, which is the assumed population mean caloric intake for Vancouverites if the null hypothesis were true, then you cannot conclude that the mean birth weight of Vancouverites is significantly different, so either higher or lower, than the mean caloric intake of the Canadian population. In this case, you would fail to reject the null hypothesis and conclude that you don't have evidence to suggest that there is a difference in the mean caloric intake of Vancouverites when compared to the general Canadian population. If your confidence interval does not include the true population mean caloric intake of the Canadian population, you should state that because the true population mean caloric intake of Canadians is not included in this interval, we can reject the null hypothesis and conclude that we have evidence to support the alternative hypothesis that the mean caloric intake of Vancouverites is different than that of the general Canadian population. Or, if you were doing a one-sided test, you would say that you have evidence to support the alternative hypothesis that the mean caloric intake of Vancouverites is lower than that of the general Canadian population. So just a quick review of the p-value. So a p-value is a probability of observing our sample statistic, or one more extreme, given that our null hypothesis is true. Another way of saying this is that our p-value tells us that if our null hypothesis is true, how likely are we to get a sample statistic that is as far or further from the hypothesized value in terms of standard errors by chance. So for example, if our p-value was 0.034, we would interpret this as, given that the null hypothesis is true, that Vancouverites and Canadians have the same or equal caloric intake, we would expect to see our sample mean of 1991 calories for Vancouverites, or more extreme, 3.4% of the time. Based on our p-value, We then decide whether to reject or fail to reject our null hypothesis. We make this decision based on our significance level, or alpha, and the alpha most often used is 0.05. And this tells us the probability that we will reject our null hypothesis when it is actually true. So if this is 0.05, then the probability that we will reject our null hypothesis when it's actually true is 5%. If our p-value is equal to or greater than our alpha, then we fail to reject the null hypothesis and do not have evidence to believe that the alternative hypothesis is true. Using our previous example, we would say that given that our p-value of 0.034 is lower than our alpha of 0.05, we reject our null hypothesis that the true mean caloric intake is 2000 and conclude that we have evidence to believe that our alternative hypothesis is likely true and the mean caloric intake of Vancouverites is not 2000 calories per day. Note that we're not concluding here that the caloric intake for Vancouverites is 1991 or that we prove that our alternative hypothesis is true, but just that we have evidence to support our alternative hypothesis that their caloric intake is different from 2000. So in the last tutorial, we discussed what bivariate data means. We also talked a bit about what parametric and non-parametric tests are, and we introduced the terminology of y equals the outcome variable and x equals the explanatory variable. We saw that we can decide which method of analysis to use based on the types of outcome and explanatory variables that we have. The type of analysis will also depend on if we are able to meet the assumptions necessary for a parametric test. If these assumptions are not met, then we must use a non-parametric test. We're now going to discuss different parametric and non-parametric tests that we use for certain types of bivariate analyses. For the different types of parametric tests that we talk about for the remainder of the course, the general idea of calculating a test statistic and confidence intervals and conducting a hypothesis test are essentially the same as what you've already learned. What's important is that you make sure that you're doing the correct test based on the research question and the available information. So for example, are the outcome and explanatory variable qualitative or quantitative? If there's a qualitative explanatory variable, how many groups are being compared? Are the groups dependent or independent? Are the assumptions met for a parametric test, or should we use the non-parametric test instead? You can use the decision tree introduced last week to help you determine which test to use. Another thing to make sure of is that you use the correct notation. And this will become more clear as we get into the differences between tests. So for example, with a paired t-test, the notation for our null hypothesis is that the differences between the sample means equals 0, while with a two-sample t-test, the null hypothesis is that there is no difference in the means between the two groups compared. So this week we're going to focus on two situations, both where the outcome variable is quantitative and the explanatory variable is qualitative with two levels or categories. We'll first discuss the paired t-test and the Wilcoxon signed rank test, which is used to compare two paired or dependent groups, and then we'll discuss the two-sample t-test and Wilcoxon rank sum test, which compares two independent groups. So this is where I think the course really starts to get interesting, in that the types of tests we're going to be using are often used in real-life applications. So before we proceed, I just want to remind you that in deciding which test to use, it's important to know if the two treatment groups, or populations, or samples being compared are independent or dependent. If the two groups consist of exactly the same people, so for example, repeated measurements under different conditions, then they're most likely dependent. This is sometimes referred to as paired. Most often, this is the same group being compared before and after some sort of treatment or experience or intervention. But another example could be identical twins, where one twin is given the treatment and the other isn't, because each twin theoretically shares much in common with the other, except for the tested categorical variable. If the two groups contain totally different people, they're most likely independent. An example of this would be comparing infected versus healthy individuals, or men versus women. So if we determine that our outcome is numeric, so for example, caloric intake, and also that our explanatory variable is categorical with two groups being compared, We then ask if these groups are paired or independent. So let's say that we've determined that we're comparing two paired groups. For example, the same group of people before and after some form of treatment. We then determine if we meet the assumptions necessary to conduct a parametric test, and if the assumptions are met, we can proceed with the parametric test, which in this case is the paired t-test. With a paired t-test, we're looking at differences between groups and apply analysis of mean of a single population. So the single population is the differences, and we're applying analysis of mean to that population. For each person, we can take the difference between their observed value from their group 1 and their observed value from group 2. So for example, the difference between their before and after treatment scores. We'll then have a single sample of observations, which are made up of each participant's measurement from group 2 minus their measurement from group 1. So for example, their after score minus their before score. We now have a single sample of these different scores for each participant. We then calculate the mean of these differences, known as D, and the sample standard deviation of these differences, and we then proceed to do a hypothesis test for a single mean and make a confidence interval. For our hypothesis test, the null hypothesis is that the difference in mean before and after treatment equals 0. Another way of stating this is that the mean difference equals 0. The alternative hypothesis is that there is a difference in the mean of the before and after treatment. In other words, the differences in mean does not equal 0. Our confidence interval is calculated in a very similar way as when we made a confidence interval for a single mean, which we've discussed in the last few tutorials. The major differences are that instead of adding and subtracting our margin of error to our sample mean, we add and subtract our margin of error from the mean of the difference in scores in our sample. Also, we use the sample standard deviation of these differences in our formula, but other than that, the formula is pretty much exactly the same. The interpretation of a 95% confidence interval would be that we can be 95% confident that the true difference in means is somewhere between the lower and upper limits of the interval. If we calculate our confidence interval and it does not include 0, we reject our null hypothesis that the difference in the mean before and after treatment equals 0, and have evidence to suggest that the differences in means does not equal 0. We can also calculate a test statistic or a t-value to test our hypothesis. So the highlighted part of the formula is the hypothesized value for the mean difference, which is most commonly 0, implying that there's no difference from the group. We subtract this from our observed sample mean of the differences, and the bottom part of the equation is the sample standard deviation of the sample differences divided by the square root of the sample size. So we divide the top part of the formula by the bottom to obtain our t-statistic. And this t-statistic tells us how many standard errors our sample mean difference is above or below what we expect it to be under the assumption that the null hypothesis is true, that the sample mean difference is 0. So now we'll turn to the assumptions that are necessary for conducting a paired t-test, or any parametric test when groups are paired. So as you can see, these are pretty similar to the assumptions for the analysis of a single population mean, which we've discussed in previous tutorials. So the assumptions are that the sample is obtained through a simple random sample, the individual observations are independent, which means that person 1, person 2, etc., and the difference in their before and after scores are independent. Something to note is that this does not mean that the groups are independent, as a critical assumption for the paired t-tests is that the groups are dependent. And the last assumption is that the sample size is large enough, so greater than 20 as a rule of thumb, or that the differences are normally distributed. If our data do not meet the necessary assumptions for the paired t-test, we instead conduct the non-parametric alternative, which in this case is the Wilcoxon signed rank test. As we've discussed previously, non-parametric tests like the Wilcoxon signed rank test do not need to assume normality, which means that they're more flexible and don't require large sample sizes. And this is because they generally deal with signs and ranks of observed values in a data set, and therefore don't need to make very many assumptions about the shape of a distribution. But non-parametric tests also have less power, which means that if a difference between the two groups, so before and after treatment, really does exist, they are less likely to detect this than a parametric test. And also, because they use signs or ranks rather than actual observed values in data, some of our information is lost. So for these reasons, we generally prefer to go with the paired t-test so that we have more power and don't lose information. But if our assumptions for the paired t-test aren't met, then we proceed with a Wilcoxon signed rank test. The Wilcoxon signed rank test uses both the sign and magnitude of differences between groups, or the difference between before and after scores across groups. This means that it not only uses information on whether scores went up or down after treatment, but also how large or how little these changes were. The null hypothesis is that the median difference equals 0, and the alternative hypothesis is that the median difference does not equal 0. This test first takes the differences in the paired observations and then ranks the absolute values from the smallest to largest. An important thing to note is that this compares the medians for each group. So for example, the median before and after score. We are usually comparing the median rather than the mean with non-parametric tests. You can read a bit more on this test and how it's calculated in the module notes if you're interested, but the most important things to remember about this test is that it's the non-parametric alternative to a paired t-test, so it's used whenever the assumptions for a paired t-test are not met. And another important thing to remember is that it makes assumptions and inferences about the median, not the mean. This is generally true of most parametric tests, that we usually make inferences about the median rather than the mean. So now we're going to discuss the case when the outcome is numeric and the explanatory variable is categorical, like with the paired t-test, but in this case, the groups with our categorical explanatory variable are independent. So in this case, the people or subjects in one group are completely different than the people or subjects in the other group. We'll first discuss the parametric test that's used in this situation, the two-sample t-test. So the assumptions for a two-sample t-test are pretty much the same as when we're doing inference for a single mean or a paired t-test. The samples are obtained through a simple random sample. The individual observations within each group compared are independent, so each person is selected independently. The distribution of observations from each group must be normally distributed, or you must take a large sample size from each group. So both groups should have a sample size greater than 20 as a guideline. And importantly, for an independent samples t-test, that the two groups being compared are independent, meaning that they contain totally different people. This is the only assumption differentiating the independent t-test and the paired t-test. And there are two possible additional assumptions that we can make when comparing the means of two groups using an independent samples t-test. Either the variation around the respective means in the two groups are not equal, or the variations around the respective means in the two groups are equal. A general rule of thumb in deciding whether or not the groups have equal or non-equal variances is that we can assume the variances of the two groups to be approximately equal if the sample standard deviation of one group is not more than double the sample standard deviation of the other group. If one group has a sample standard deviation more than double that of the other group, then we will have to assume that the variances in the two populations are not equal. So first we'll talk about when the two groups have non-equal variances. So as I mentioned, we conduct a two-sample or independent samples t-test with non-equal variances when the sample standard deviation of one group is more than double that of the other group. The null hypothesis for this test is that the mean of group 1 minus the mean of group 2 equals 0. In other words, that there is no difference in the means between the two populations. The alternative hypothesis is that the mean of group 1 minus the mean of group 2 does not equal 0. In other words, that there is a difference in the means of the two populations. The confidence interval is similar to other calculations of confidence intervals, except in this case, the mean is the difference in the sample means. Our t-value is calculated the same as previously, except that our degrees of freedom is the smaller sample size of the two groups minus 1. To get the standard error that's used in the calculation of confidence intervals in this case, we add the variance of group 1 divided by the sample size of group 1 to the variance of the group 2 divided by the sample size of group 2, and then we take the square root of the sum. The calculation of the standard error when the groups compared have equal variances is calculated differently, as we'll see shortly. If we calculate a 95% confidence interval, our interpretation would be that we are 95% confident that the true mean of group 1 is somewhere between the lower and upper limit units, lower or higher than group 2. If this confidence interval crosses 0, we fail to reject our null hypothesis that there is not a difference in the means between the two groups. If this interval does not cross 0, we reject our null hypothesis and conclude that we have evidence to suggest that there is a difference in the means of the two groups. We can also calculate a test statistic, or a t-statistic in this case, to test our hypothesis. The part of the formula on the top, y bar 1 minus y bar 2, is the difference in the sample means. Our hypothesized value for the difference in the sample means is 0. So we plug in these values and divide this top part of the formula by our standard error to obtain our t-statistic. This t-statistic tells us how many standard errors our observed difference in means is above or below what we expect it to be, under the assumption that the null hypothesis is true, that there is no difference in the means of the two populations, that the difference in means between the two populations equals 0. We'll now discuss the two-sample t-test when we assume equal variances, the situation when the sample standard deviation of one group is not more than double the sample standard deviation of the other group. The null and alternative hypotheses are the same as an independent t-test with non-equal variances. The calculation of a confidence interval and t-statistic are pretty much the same, except for two main differences. First, as I mentioned previously, the calculation of the standard error for the difference in means is different. Assuming equal variances means that we believe that the variation around each group's mean is roughly the same. So in other words, that the standard deviation of group 1 and the standard deviation of group 2 are two different estimates of the same thing. So in this situation, we take a pooled estimate of the common variance, which means that we take a weighted average of the two estimates of the variance from each of the groups in order to calculate the standard error. The other difference is that when assuming equal variances, our degrees of freedom is calculated by adding the sample sizes of the two groups together and subtracting 2. Our calculation of the t-statistic is the same as when we assume non-equal variances, except that we use our estimate of the pooled variance for the standard error portion of the equation in this case. And the interpretation of our confidence interval and the t-statistic are the same in this situation as when we assumed non-equal variances. The last test we're going to talk about in this tutorial is the Wilcoxon rank sum test. This is the non-parametric alternative used when the assumptions for a two-sample t-test are not met. The Wilcoxon rank sum test is similar to the Wilcoxon signed rank test, but these two tests are not the same. The Wilcoxon rank sum test is a non-parametric test for the equality of two medians when the groups are independent, while the Wilcoxon signed rank test is a non-parametric test for the equality of two medians with paired or dependent groups. As with all non-parametric tests, this test works with the ranks of observed values rather than the values themselves, and therefore makes few assumptions about the distributions we're using, which is a strength. But this test is also less powerful than the two-sample t-test, which is a weakness. The null hypothesis is that the difference in the medians of the two groups equals 0, while the alternative hypothesis is that the difference in the medians does not equal 0. So let's turn to an example. Collect a simple random sample of undergraduate students and take a simple random sample of graduate students and measure their caloric intake. Is the caloric intake of undergrad students different compared to grad students? Assume normal distribution of data. Which test should we use? So our outcome is caloric intake, which is continuous, and there are two separate groups being compared with our explanatory variable. The groups of undergrad and graduate students contain totally different people, so they are independent groups. Because the distribution of the data is normal and these individuals were independently and randomly selected, our data meets the necessary assumptions, so we would use an independent samples t-test. The next step would be to determine whether the variances for caloric intake were equal or not equal for undergrad and graduate students. And then as a final step, we would determine whether we should conduct a two-sample t-test with either equal or non-equal variances. So let's try another example. 100 randomly selected people had their blood pressure measured. Then the same 100 people were given treatment and their blood pressure was measured again. Is there evidence that the treatment reduces blood pressure? Which test should we use? In this case, we're looking at the same people and looking at their blood pressure before and after the treatment. So we have paired data. The data come from a large sample, and this is a simple random sample, so our data meets the necessary assumptions, and we would conduct a paired t-test. Here's another example. A random sample of 28 men was obtained with a mean resiliency score of 19.93 and a sample standard deviation of 1.51. A random sample of 25 women was obtained with a mean resiliency score of 12.07 and a sample standard deviation of 1.25. Is there a difference in the mean resiliency score of men and women? Assume normality of data. Which test should we use? And calculate a 95% confidence interval for the difference in mean and interpret. So again, our outcome is numeric and two independent groups are being compared, men versus women. The data are normally distributed and are derived from a simple random sample. So we would use a two-sample t-test since we're comparing two different groups. The standard deviation of men is 1.51, while the standard deviation of women is 1.25. Since one of these standard deviations is not more than double the other, we would conduct a two-sample t-test assuming equal variances. The next part of the question asked us to calculate a 95% confidence interval for the difference in means as a hypothesis test and to interpret. So we follow all steps for hypothesis testing. The null hypothesis is that there's no difference in the mean resiliency scores of men and women, and the alternative hypothesis is that there is a difference in the mean resiliency scores of men and women. The assumptions are met, these samples are obtained through a simple random sample, the individual observations within each group compared are independent, so each person is selected independently. The groups are independent, and the data are normally distributed and come from large samples. The next step is to calculate our confidence interval, which we use the formula for a two-sample t-test with equal variances. We first calculate our pooled variance by plugging in our values for the sample sizes and standard deviations for each of the two groups. And once we do that, we plug our pooled variance into our formula and weight it by the sample size of each group to calculate the standard error. Our degrees of freedom is the sample size of group 1 plus the sample size of group 2 minus 2, which equals 51. And when conducting a two-sided test with a level of significance of 0.05 and a degrees of freedom of 51, we determine our t-statistic to be 2.009 and then calculate our confidence interval. And note that instead of using a t-table, we could instead use a z-table to get our z-statistic of 1.96, which will give us approximately the same result. And then the interpretation of our 95% confidence interval is that we are 95% confident that the interval 7.10 to 8.62 contains the true mean difference in mean resiliency scores for men and women. Or we can say that we are 95% confident that the true mean resiliency score of men is somewhere between 7.1 and 8.62 higher than women. Given that this interval does not include 0, we can reject the null hypothesis that the mean resiliency scores of men and women are equal and have evidence to support the alternative hypothesis that the mean resiliency scores of men and women are different. Note that by using confidence intervals here, we are not only able to conclude that there is a significant difference in resiliency scores, we are also able to quantify how large that difference might be. This is why confidence intervals are more informative than hypothesis tests. In our next tutorial, we'll introduce one-way ANOVA or analysis of variance, and learn how to check assumptions and talk about the different sources of variation in our calculations, as well as the F statistic.